lecture of Joaquin. So,
okay,
please start.
Okay. Yeah, thank you. Can you see my my slide?
Yes.
Yeah. Okay. Thank you. Okay. So yeah, I was talking about the near extremal BTC. So you do KK reduction in the throat, and you get a dilaton gravity that I have here, and with this U1 gauge field. And okay, so this is something we studied in a paper. I mean, okay, this was solved in a lot of other papers, but the approach we took with Ghosh and Maxfield in a paper from last year is to first integrate out the gauge field. And this is easy to do in 2D because it's like 2D Young Mills and you know how to solve it. And all you need to know for the purpose of the lecture maybe is that you can choose boundary conditions of fixed charge, in this case fixed J. And then the only effect of integrating out the gauge field is to add a local term in the action, which is this one, that shifts the dilaton potential in a charge-dependent way. Then when we are near the horizon, we need to take the dilaton and put the extremal value. From 2D, the extremal value comes from the equation of motion, which is that the potential is 0 when evaluated on a constant dilaton background. And then you look at small fluctuations. And this little phi is what I would call the JT dilaton. And this phi naught is what multiplies. So when you put this expansion in the action and you expand to linear order in phi, you get a topological term proportional to phi naught in this way. And this is just the Bekenstein-Hawking because phi naught is the size of ds1. And in terms of the charge is given by this. And then the linear term is the JT gravity action. And further non-linearities in phi are suppressed in S naught, in 1 over S naught. So this is another reason why it's hard to argue of trusting non-trivial topologies, because when you add non-trivial topologies, you cannot neglect the fact that the potential is not exactly JT, and all the also contributions from KK mode start mixing, and then it's a little bit more complicated. So we'll look just at the disk, at the Euclidean black hole geometry. So then we claim that the BDC partition function is approximately given by this term. So this comes from, this is the topological piece, and this comes from the action evaluated in the asymptotically ADS3 far away region. And it's a little bit non-trivial, like why here I have the extremal mass and not the mass corresponding to this temperature. But this is the right answer, and you have to look at the boundary terms, etc. That this is worked out in this paper from last year, for example. But the idea is that we will treat the far region classically and just include classical fluctuations coming from the fact that we are at finite temperature, but not quantum fluctuation. And this is an approximation that we will see that is well defined, is good approximation. And then we multiply this by the JT partition function. And the boundary conditions are fixed in the throat by just propagating the boundary conditions that you put in ADS3 to the throat. And then you'll see that the dilaton should be fixed to this. So epsilon basically parameterizes at which point. So let me see. Epsilon is the position of this blue line where you glue the throat with the far region. And if this is very large, then the answer will be independent of. So there is a region here of overlap of the ADS2 cross S1 geometry with the BTC geometry with the 3D with the extremal answer. So we will put a cutoff here where we glue, and the answer will be independent of the precise position. And in 2D, this is the fact that the partition function is independent of epsilon, and it depends only on the renormalized values. So the renormalized dilaton is proportional to the central charge, and this central charge arises from this factor of G Newton that I put here. And the length is proportional to the ADS2 radius and the renormalized length of the thermal circle in the asymptotically ADS3 boundary. So this is what the 2D CFT would call beta. Then the contributions from KK mode are suppressed, and also their interactions are suppressed. And one quick way to see it is that the matter action, when you dimensionally reduce, everything gets multiplied by phi naught, which is the volume of the transfer space. And when you canonically normalize fields in the correct way, basically all the interactions will come suppressed by factors of phi naught. Or in other words, maybe this counts the loops of matter loops from matter interactions, and this is very large, so you can ignore them. Okay. Now you can compare this classically. You can compute the classical partition function of.
Can I ask one question? In the previous slide, I mean the boundary condition you use at the boundary of ADS slot is basically corresponding to kind of the Dirichlet boundary condition where energy is totally reflected at the cutoff in some sense. What I'm saying is it's not transparent, right? The boundary condition you use.
Maybe you're thinking about the matter.
What I'm saying is no. What I'm saying is this ADS cutoff at the ADS cutoff, where you are considering in such a way that the world two-dimensional space-time is ending there. It is not connected to the asymptotic region in some sense.
No, I think it is, because so I imagine that I have this is a flattened version of the cigar geometry, let's say, and then what I'm doing is just looking at some patch very close to the Euclidean horizon, and what I'm saying is that in this region,
energy, for instance, I mean, if one consider extension in this near horizon sort of, the energy stays there or it can come out. For instance, if one considers scattering event, scattering event there to the this cutoff surface, then energy comes out in a transparent way, or it reflected back.
No, in a transparent way. So
I mean, you are ending the world there.
Not really, because when I write this formula, I'm gluing this to the outside, and things can propagate from here to there transparently. That's the idea. So maybe it's
not it's not JT in a certain sense, because I mean it is connected to the outer world.
Okay, maybe, I don't know. I mean, maybe another way to say it is that we want to do the Euclidean path integral in this whole 3D geometry, and we just cut two pieces, this and the other one. The part here is classical, and so I'm just reading off what boundary conditions are derived in the JT region from the ADS3 boundary. Yeah, but if I look at matter, for example, it can propagate everywhere. It's not reflected on it.
Okay. Go ahead.
Okay. Yeah. So
sorry, Joaquin. Sorry, I also have a question. So, so this classical term that you say there, I mean, you put in front of the path integral.
Yeah.
So this essentially, isn't it like, I mean, the classical action, right? I mean, in that region, in the asymptotic region?
Not quite, because you have the Gibbons-Joaquin term in the box. So, okay, let me draw it like this. So you have, let's say here, this is the JT. and this is the asymptotic. So it's the classical action evaluated here, but
right.
So here in JT we put the Gibbons-Hawking term, and then
Sure.
when you
Well, also in the
yeah, so then you have to put the Gibbons-Hawking term here to be consistent. When you compute the action here and you include the Gibbons-Hawking term in this boundary, it gives you the extremal energy. What I mean is, because if you would just compute the classical path integral without this subtlety, you wouldn't get the Euclidean energy, the extremal energy. You would get the energy that corresponds to this inverse temperature.
right.
But that correction will come from the JT mode instead.
Right.
Yeah.
So and why why do you separate into this Joaquin Teitelbaum part and this asymptotic classical region?
Because the physical picture that I think that we are trying to say is that all quantum effects are restricted to this region, and when you send the temperature to 0, the central charge will be large, so there is no we're not going to look at finite GN effects, but so in that sense this region is completely classical, there is no correction. But when you look at very low temperature, there will be large quantum effects near the horizon. So we're separating the region where there is no enhancement of quantum effects at low temperatures to the region where there is an enhancement of quantum effects that should be treated separately.
Right. So if you just, I mean, if you didn't do the separation and you just did the path integral, I mean,
yeah,
would there be a problem? Like, I mean, from the beginning?
No, it's just that maybe the quantum effects outside. So for example, I was talking about the KK mode. So if I try to reduce them here, then the dilaton varies too quickly. And you'll get action for this matter that is not going to be very, yeah, it's harder to argue that the KK modes are suppressed and the,
I see, okay.
Yeah, you know what I mean? The kinetic part of the matter fields will look weird in that region, but the point is that you shouldn't, it's not necessary to compute their quantum effects outside anyways, because I don't know, they're suppressed by G Newton, but they don't get enhanced at low temperature. Yeah.
Okay, thank you.
Yeah. And maybe to show, so what I wanted to do first to show that this makes sense, at least one example where hopefully will become clear that this makes sense, and why we chose 3D gravity is that you can do the path integral exactly, including quantum effects in 3D for pure gravity everywhere. And then we will see that answer matches with this approximation of cutting and gluing the far away with the near horizon. So that, okay, maybe we can talk later about the interpretation, but at least that should convince you a little bit that this is a reasonable thing to do. Okay, so the first comparison is the classical partition function. And if you can compute the classical action of the BTC black hole everywhere without cutting, and you will get this. And this is precisely has the form that I just wrote. So this is S naught. Maybe let me write it. This is S naught. This is E naught. And this term is the JT classical term. Is the classical action of JT gravity with the boundary conditions that I just described. But this formula was obtained from the 3D action of the BTC black hole expanded at large J and small temperatures. Okay. So as I said, we can do the same. The exact partition function for pure gravity was computed by Maloney and Witten, and is given by this answer, written in terms of the moduli of the boundary torus. And this is basically the vacuum character. And this calculation was checked in several ways, in a lot of ways. At least I know 3 ways of computing this, and they all give the same answer. So I will take this to be the full quantum path integral around this BTC background. So it doesn't include higher topologies. It's just quantum fluctuations around the disk, let's say. And if you take the near extremal limit of this formula, you get this. And this is precisely consistent with what I just said. So this term is coming from the far region. This is let me call it far. This is the JT term. And this is the JT, let's say, quantum term. So if I will compute the partition function using this prescription, then I will have written here the exact JT partition function with these boundary conditions, and you will have this form again, like this gamma over beta, where gamma now is this combination. And what I'm trying to say is that that matches precisely with the limit of the exact 3D calculation here. And up to a small subtlety that you have to shift the extremal entropy in a way that this is very well understood. So this just comes from doing the path integral in rigid ADS2 without including corrections of finite temperature. And this is the calculation that in higher dimensions Ashok Sen would have computed. And this 1/2 as well comes from the same reason, comes from one loop effects of the graviton. But the point is that the temperature dependence that will fix the density of states is coming purely from the JT gravity mode. So when I talk about JT, I will focus on the temperature dependent piece and not worry about things that are temperature independent. But you can also integrate out the so what I'm trying to say is that these terms are understood from integrating out the KK modes, and they give contributions. Matter, KK modes, they give contributions that are temperature independent. Okay, so when we extract the density of states from that formula, we get back, of course, the Schwarzian answer at fixed. And it's important here that we picked fixed angular momentum. If we would have picked fixed chemical potential, then it would be a little different. And the density of states as a function of energy behaves as an exponential at large energies of square root E. This is the Cardy growth that you would have guessed without taking the near extremal limit, and then goes smoothly to 0 at in this way. And this gap energy is of order 1 over gamma, in our case 1 over C. And I call it a gap because that's the name that people gave it in the 90s, where they argued that the statistical mechanical description of black holes fails at low temperatures. And the reason that they gave was that, so if you remember, the change in energy goes as T squared. So if you go at very low temperatures, the energy of a Hawking quanta that is of order the temperature is bigger than the near extremal energy of the black hole. So in a way, sending one Hawking quanta can produce a large back reaction in the geometry. That's kind of the picture that these authors gave, and especially some work by Wilczek afterwards. So, and you can see that very clearly here, where as you take the temperature to 0, quantum effects from the JT mode are becoming enhanced and can change the spectrum a lot, even though you are still at large central charge. But the picture that these authors or the afterwards gave, coming from string theory mostly, is the idea that the resolution of this is that there is a gap at the scale 1 over gamma. And actually that you don't have any state in this region. But in this calculation, we see that the resolution is different. The density of states goes smoothly to 0. And what you thought was the entropy of the extremal black hole is actually much smaller than that. But there is nothing wrong with the Bekenstein, or maybe the lesson here is that the Bekenstein-Hawking is not the right prescription to count microstate, it's the Gibbons-Hawking, which means do the Euclidean path integral with the right boundary conditions. And that has been checked in a lot of ways. For example, in general, that prescription tells you that semi-classically, that's given by the minimal area or in general by the Ryuta Kayanagi, or in the case of the black hole, that would be the area of the horizon. But I think that the lesson here is that you can have cases in which even though Gn is small, you can still have quantum effects that give you an answer that deviates from the area, but it's still given by the prescription of the Euclidean path integral. Okay. And okay, as was anticipated before, this picture will change when we add supersymmetry, and that will explain why this is not inconsistent with the countings that were done from string theory. Okay, so okay, we can do the same with correlators. And
well, can I check
yeah.
one point in your previous slide? So so the argument about the gap, I mean, the one Hawking quanta can destroy I mean, can destroy this ADS2. So that argument, you would like to say that argument is not precise, or?
No. What I'm saying is that the resolution that people thought, so no, that argument is precise, and I think I think this calculation makes it even more precise and shows you how you have large back reaction when the temperature becomes too low. So the fact that the JT mode becomes strongly coupled at low temperatures shows you that their intuition was correct. But now there is a second question, which is what is the resolution of that? So what is the picture of the density of states? And the picture that I feel people had in the 90s looking at papers, I mean, I wasn't working on this back then, is that based on examples from string theory, they assume that there is always a gap. That you have a gap and then you have a large e to the s naught states exactly at extremality, then you have a gap and then you continue. And what I think this calculation shows is that picture is not correct. The resolution is not correct.
So it is strongly coupled there, but we don't need the gap. That's what you would like to say.
Yeah.
Okay. Thanks. Thanks a lot.
Yeah, sure. And maybe you could have seen this even without talking about JT gravity, right? This is the same that you would derive from the exact pure gravity path integral in 3D. So just to strengthen the argument or the conclusion. Okay. But of course, the idea is that this is a generic behavior in this regime, a generic behavior of near extremal black holes. But okay, so so the last comment is that we can do the same with correlators. This is easy in 3D, but might be harder in 4D or in higher dimensions. And the idea is that we will again glue the physics in the throat that we get from JT gravity coupled to free fields to the region far away region outside the throat that we glue to the ADS3 boundary. For simplicity, we can compute S-wave correlators, meaning that we will integrate them in space. And the higher partial waves, meaning if I would add, for example, e to the IK5, then we will have a U1 charge related to K. So they are just charge fields under the U1. Okay. And these fields are free to propagate transparently everywhere. The boundary conditions for the matter are chosen such that this blue line is a transparent. So it's not a physical separation, it's just for the calculation to cut and glue. Okay. And from this calculation of separating in the near horizon and the far region, you can derive that the correlators in the BTC geometry are very simply related to the correlators computed in ADS2. And there is the only difference is a simple prefactor that comes from the contribution in the asymptotic region. And this is computed by the Schwarzschild theory with IR dimension given by. So the UV dimension, so H is the, well, okay. Here I'm talking about the scalar field. So in 3D, it will have dimension H right moving and left moving dimension h. So the UV dimension will actually be 2h, but the IR dimensions is half of it. That's what it is. And semi-classically, this, for example, if you look at the 2-point function, you will get this. That this is just the near extremal limit of the 2-point function you will compute in the PTC, and you took the extremal limit, and you will get this automatically. And from the EDS2, this is the semi-classical answer that I explained yesterday that you will get if you do compute 2-point functions in JT gravity. But this argument, what we argue is that this argument is valid beyond the semi-classical limit, and you can trust quantum corrections to the Schwarzschild correlators as well as approximations to the 3D correlation functions. Okay, and so that's an argument from the bulk that you can trust them. And what I will explain next is that you can see this from the CFT by a modular bootstrap argument, where we will find the universality of the partition function of correlate and correlators of any CFT and their general conditions that will be consistent with the argument I just gave from the bulk. Okay, so that's the question I just did, and the answer is yes, and the assumption is to have a twist gap and large C. And we will reproduce the exact Schwarzschild correlators, including quantum effects. Okay, so going back a little bit to some conventions. So the Euclidean time in the boundary is TE, the spatial circle is phi. And I will look at the boundary torus like with this identification. So beta is the inverse temperature and theta is the chemical potential of angular momentum. The partition function is given by this trace over the Hilbert space. And again, it will be useful to write it in terms of Q or left and right moving temperatures. Yeah, it's also useful to introduce the parametrization of states in 2D that is very familiar from Liouville, where the central charge will be parameterized in terms of B. So Q, big Q will be B inverse plus B, and the C is given by this formula. So large central charge means to take B small. And the dimension, scaling dimension H of operators will be parameterized in terms of P squared in this way. So if I take real P, then I have operators of dimension bigger than C over 24 that are along this line. And if I have P complex, I can make like operators of dimension from 0 to C minus 1 over 24. And this, so it's okay, it's convention to introduce this parameter alpha by this formula, and light operators correspond to real alpha, while heavy operators correspond to real momentum P. This is momentum in the Liouville, just the words, but it's convenient to write the formulas in terms of that. Okay, so the near extremal limit is to take, as I said, large central charge, and then we will take large left moving temperature of order C. And the reason we take it of order C is that, as I said, the gap, quote unquote, temperature is 1 over C. So that's the temperature at which quantum effects become important. So we want a temperature where you can really test whether you are getting the right quantum corrections or not. If you would take large beta but order 1, you might be in the semi-classical JT region. So you really need to take beta to be very large to see the quantum effects. And okay, and the right moving beta will be taken to be very small, and basically beta R small corresponds to the large angular momentum, and the large beta left corresponds to the low temperature. And okay, you can go from the fixed J to fixed chemical potential ensemble in this way. And in terms of fixed charge, this is the same as I said before. So beta of order C and very large angular momentum. Yeah. So we want to compute the partition function in this limit, and the idea is to use modular invariance. So modular invariance tells us that we can expand in the dual channel. So we do before we were quantizing on the circle, on the spatial circle, and it tells you that now you can quantize on the Euclidean time circle and look at states propagating perpendicularly. And this gives you an expansion of the partition function as a sum over primaries in this dual channel. In particular, you have the vacuum and you have higher order terms. Now, the point is that if there is a twist gap, meaning that, okay, I will say in a sec what it means, but with the assumption of twist gaps, you can argue that when you're looking at very large beta L and small beta right, only the vacuum dominates, and you get this. So this is kind of a Cardi argument with the subtlety that, so how does it work? So I'm taking beta right to be very small. So I'm taking right moving temperature to be very big. If I go to the dual channel, I'm looking at the right moving temperature very low. And that picks the vacuum to dominate in the right moving sector. So I have a state with H right equals 0. What the twist gap tells you is that there is no state with HR equals 0 besides the identity. And that's important because in the left moving sector, we are looking at low temperatures in the direct channel. So in the dual channel, we are looking at large temperatures. So from the left sector perspective, there is no argument that the identity dominates. And it's important. So then the twist gap tells you that if the right moving sector tells you that HR is 0, then the only state is the vacuum. That's the idea. Is this clear? I mean, it's hard to say in words, but it's not very. Okay. Okay, so now okay, at this point we are done. So this is the same as the Maloney-Witten partition function. So you could say we take the near extremal limit again, and we will get the same answer. And that's the JT partition function. So just to tell a little bit more details of how this limit works. So as I said, in the dual temperature is a low temperature limit of the right moving sector. So we have only the Casimir energy. That's all, the vacuum contribution. And this is basically the term that will when you change ensemble and you write it in terms of J, this produces S naught, basically, the extremal entropy. Now the left moving temperature is at the left moving sector is at high temperature in the dual channel, and this means that descendants are not negligible. We need to sum over descendants. And to do this, the simplest way is to use the modular transformation of the characters. So this should be interpreted as the character in the dual channel, and this in the original channel that we wanted to quantize in. And this relation can be shown, well, there is an explicit formula for this character, so you can show it. And this modular S matrix has this form. And in the right-hand side, this is in the direct channel, we are looking at low temperatures, so the descendants are negligible. And for convenience, we will write it in terms of P, of the momentum of the state. And the point that here is a sum over real P means that when we look at it in the direct channel, we only have states with HL bigger than C/24. And when you take into account that the left moving temperature is of order C, you will get that only states with P/B fixed contribute in the near extremal limit. And if you remember, B goes to 0. So in terms of the left moving dimension H, we are looking at states that are very close to C/24, that have dimension C/24 plus something that is of order 1/C. So these are very close to, very near extremal states. Yes. Okay, so sorry, this is a little technical, but putting all the pieces together, the left moving block is given by this. We're here basically the cinch. So let me go back. If I parameterize things in terms of K, which is P divided by B, then you see this is just K, this is cinch of 2 pi K. And this is approximately K, basically, with some powers of B. And here, when you put it here, this will be K squared. So K squared is what we would call the Schwarzschild, or the energy in the Schwarzschild sector. And from here, which is this formula I wrote here, you get precisely the density of states from the Schwarzschild density of states. So these are all the factors that come from taking the limit. And so here the idea is that we will call this E of k, and then this is dE, and then this is the sinh of square root E from the Schwarz. So here I'm just re-deriving what I said before in a different way. And if you integrate over k, or equivalently integrate over energies, you get again this this partition function. So this is the shift of 1/24 that I mentioned, and this is the Schwarzschild classical piece, and this is the Schwarzschild one loop term. Okay, and now I was talking about the left moving sector, but now you can put everything together and talk about the total energy and the total angular momentum, and you get precisely this formula that I wrote before. That before I wrote it as a function of beta, but now I wrote it as in terms of the density of states. And this is precisely okay the Schwarzschild one. So it's all things I already said. But now this is true for, so we show that this is true for any theory with large C and a twist gap. The density of states, the near extremal states are described by the Schwarzschild theory. So this is very, just want to stress that this is very universal. And again, there is no gap, as I mentioned before. That conclusion is still true here. So now I will talk about correlators. And here I have some slides in the website that you can look at, but I think I will go over it quickly, not to bother you. And also it's a very similar argument to the partition function, only a little bit more complicated, but moral is the same. So the idea, we will look at correlators at very late times and at fixed angles, and then we will integrate over the angle. So it's useful to look at it in terms of the left and right moving cross ratio, or not cross ratio, I mean, so here C is like T minus pi plus pi, sorry. And this is T minus pi. So we will take T to be of order C and phi to be of order 1. But we will choose some, so phi is 2 pi periodic, but we will add a phi, some integer number of 2 pi to make C bar be between 0 and 2 pi. And then Z will be large and will be proportional to 2 times T. Okay, this is, okay, just looking at the kinematics. My point is just that the left moving cross ratio will be large of order of the time separation, and the right moving one would be order 1. And again, if we do a modular transformation in the 2-point function, we will look at the torus that has this shape. So this circle is the spatial circle, and this circle is the time circle that has size beta right. And the idea is that the identity channel dominates in this region, and in this region we have, if we insert an operator O, the operator O propagates here. And okay, this is easy to compute. This conformal block just gives you this. So this looks like a right moving 2-point function, where here you have the minimum between C bar and 2 pi minus C bar, because if I take these two operators and make them far apart, at some point this O will dominate in this channel, and the identity will be here. So what I'm trying to say is that the identity propagates along the segment that has shorter distance. Longer distance, because it's more energetically favored. And once we look at the right moving sector, we decide that we have the identity here, that will tell us that we'll also have the identity in the left moving sector because of the twist gap. And let me just go to the end. This is just, so, okay. So when we look at the left moving sector, we also have the identity, but now there is no again, the justification is through the twist gap because this is a high temperature limit from the left moving perspective. And so we need a 2-point torus block, and this is hard to compute, but the idea is analogous to the partition function. We do a modular transformation back to the original channel of only this block. And when you go to the original channel, you can neglect descendants. And the subtlety is that you have to do a modular S matrix to do that modular transformation, and this is this factor. But you also need to do a fusion transformation that I'm not going to explain, but it gives you this other factor. And this factor is just the conformal block in the direct channel that is just a scaling block, just an exponential with no descendants. And when you get to this point, you will see that you have an integral over things that look like energies with a JT density. So this gives you a JT density of states for the same reasons that I explained before for the partition function. This is a thermal Boltzmann factor. And if you remember from yesterday, this term that comes from the fusion matrix is precisely the 2-point function derived from the Schwarzschild theory. So maybe this is, so when you go through the details, you can appreciate more how non-trivial it is to get this, than if I just tell you the answer, but it is. So this is precisely the Schwarzschild 2-point function. But okay, this is not yet. We still need to put the right and left mover parts together. But the idea is that, so what I just wrote gives you the left moving block. And now, as I said, the left moving coordinate is just twice the time. The right moving one is the angle. So when we integrate over the angle, we are just kind of forgetting of the angular dependence of the left moving block and just integrating the right moving block. And when you do all this, you get precisely the right answer. And another check that we did is to be careful about the prefactor that is sitting here. And if you are careful about that prefactor, you'll get that it matches with the ones that you derive from gravity. If you remember, there is a prefactor that comes from the faraway region where we glue. Part of it comes from the faraway region, part of it comes from the integration over the angle. And the thing you derive from the 2D CFT argument matches with the gravity calculation. And this implies that so this implies that the correlator that decays exponentially at very late times, you can trust the power law decay that we derive from the Schwarzschild. This is also true for the CFT correlators. And this, actually, I didn't put the reference, but these power law decays were observed numerically by Kaplan and collaborators when they look at the late time behavior of vacuum blocks. So I think this gives a nice interpretation of those power laws as near extremal states. Okay, we can do the same for the 4-point function, although it's a little subtle, but the point is that we take two pair of operators A and B, and we choose them to be, this is the right moving torus. We choose them to be close to each other in pairs so that we can justify that we have the identity propagating here and here, and so that the channel is trivial. I'm saying this because when you integrate over the angle, you might also have configurations where all the operators are close to each other, and then here you can have more non-trivial states propagating. But you can argue that these contributions are subleading when you compute the integral over angles, and that all the leading contribution comes from this diagram. And when you have this diagram, you can do the same modular transformation, fusion matrix, and you will get the Schwarzschild 4-point function, or the JT gravity 4-point function, including quantum effects. So in particular, this argues that you can look at out-of-time order correlators, and you can argue that they have maximal chaos. So there is a large class of CFT that are maximally chaotic when you look at near extremal states. And this is interesting because this this justifies a little better. So there was an argument of Roberts and Stanford saying that if you have a twist gap, then theory is maximally chaotic, but that argument was not completely rigorous. And I think this one is a little bit more rigorous because they look at general states, but if you look at near extremal state, you have an extra parameter, which is the angular momentum that okay, when you look at the details, it makes things more under control. But okay, and this is related to the gravitational S matrix in the bulk. This is an okay. So as a brief summary, so a large class of 2D CFT have universal Schwarzschild sectors, and they all match with this interpretation that in the near extremal BTC has a long nearly ADS2 throw. Okay, so in the last part of the talk, I will talk about pure 3D gravity. And the idea is that Maloney and Witten proposed to define pure gravity as a sum over classical saddle. Yeah.
Ask a question?
Yes.
Regarding this computation of 2-point function and 4-point function, basically you find the match with the Schwarzschild computation.
Yeah.
Can you clarify? Maybe you already mentioned about this, but can you clarify the validity regime of this agreement? I mean the validity regime of the agreement.
Yeah. So in terms of the state, this is true for states that are very close to extrema, and let me see. Let me go back to the slide. So I said that in the beginning when I said about what I mean by near extremal limit. So here. So let's take for example here. So when you look at states where the temperature is of order C, and you look at angular momentums that are very large. And this depends on the gap. If the larger the gap is, the twist gap is, the lower how do you say? If the gap is large, you don't need the angular momentum to be very large. But if the gap is small, you need to go to very higher. So this kind of depends on how big the twist gap is. But if you assume it to be much larger than C, then you're safe for any theory. So if you translate this in terms of states, we are looking at states with large angular momentum and energy that are very close to the where energy very close to J and J large.
I see.
And if you look at the correlator, we are looking at correlators at late times, so times that are of order C. You can also look at times that are very large of order 1. Then this is also true. But then you're not going to see the quantum effects.
So basically, you get this continuum density of state by taking C very large. Is that?
Yeah, so there should be effects that maybe, or I would say it's both C and the angular momentum. But the level spacing, probably, if you, well, yeah, I mean, then maybe you go into this Tauberian theorem questions of how much do you have to average to try to trust Cardi-like formulas. I mean, I don't want to go in that direction because I don't know too much about it, but if you assume the theory is chaotic and maybe you can say that the level spacing is of order e to the minus s naught, and that's suppressed by both the central charge and the angular momentum.
But we don't need any ensemble average interpretation here, right?
No, I'm still talking about the disk, this part.
Oh.
Yeah. I was going to talk about some applications that involve our topologies now, but so far all this discussion was in the disk. Yeah. Okay, so I will go to, okay. Okay, so I will go a little quick. Yeah, I guess I didn't notice. Okay. Okay. So the what I'm going to talk now is about pure gravity. So now pure 3D gravity, and Maloney and Witten proposed to define it as a sum over classical saddle with quantum fluctuations. So we sum over fluctuations only around geometries that or we integrate over metric that are continuously connected to some classical configuration. So if we want to compute the pure gravity partition function with the torus boundary, like we have been working, then we want to integrate over geometries that fill that torus. These are the BTC black holes, but include quantum fluctuations. And the main question is, following holography, can this be interpreted as a trace over a Hilbert space that is unitary and compact and all that? So the saddle points are given by the SL2C black holes, and the full partition function, including quantum fluctuations, is given by this formula, which is a sum of so these are the vacuum character, and each SL2C black hole partition function is basically the vacuum character evaluated at this SL2C transformation of the modular parameter. Okay. And if you inverse Laplace transform that, you get a spectrum that looks like this. So you have pure ADS3, you have the extremal black holes, and then you have states that are continuous but discrete in the spin. So you only have integer spin, but other than that, you have a continuous spectrum. So this has three problems. First, the spectrum is continuous. Second, there is a negative density of states, both at spin 0 here, and also very close to extremality. When you look at rho very close to extremality, it becomes negative, and this was observed last year by Benjamin, by this group. So, okay, so in a paper with Maxfield, we wanted to apply some of the things about JT gravity to this problem, given that the problem arises very close to extremality. The idea was, can we take ideas from JT gravity and understand how this can be resolved, this negative density of states. And an important point is that when you look at these SL2C black holes and you look at their throat geometry, the geometry becomes ADS2 with a conical defect, which is this. So this is in some coordinates. The metric in the throat is given by this and this. So C and D are the parameters of the SL2C black hole, and it tells you which cycle is getting contracted in the bulk. And the fact that this is 1/C and not 1 tells you that there is a conical defect. And this picture was also appeared before when counting n equals 4 dions in this paper, and it has some interesting physics there. And this geometry has a singularity in 2D, but is regular in 3D. And the reason is that, so for example here, I show one example. If this is the horizon, then we identify these two segments. This is the case with the leading SL2C black hole. But when you go from here to here, the reason why the 3D metric is smooth is that you are going to different spaces in DS1. This is DS1. And to go back to the original point in S1, to go back here, you have to go twice around the defect. So this is the case with C equals 2. And where C and D are the SL2C parameters. And when you go to higher images of SL2C black holes, then the angular deficit becomes smaller, and it depends on these parameters C and D. And from JT gravity, the idea is that when you reduce on this gauge field, you get a singular thing. You get a monopole. It's like inserting a monopole of this gauge field. And this is kind of like the Kaluza-Klein monopoles that one can also encounter in higher dimensions. So, okay, if you look at the density of states of BTC, this is what I wrote before, the Schwarzian answer. And if you look at the leading image, this is from a 3D calculation, you get this. And this is precisely the partition function of JT gravity with one defect. So this was computed, this formula by this group. Or actually, their formula is valid in a bigger regime, but if you take their formula in a near extremal limit, you get this. And the important thing is that this, that is proportional to what I will in 2D we will call the fugacity of the defect, can be positive or negative depending on the angular momentum, if it's even or odd. And the negativity that they observed, and this is what I mean by EJT, so this is like, I'm removing the extreme. If you look very close to extremality, so you send this EJT to 0, which means E is very close to J, then this factor blows up. It goes to 1 over square root E. And this factor makes it negative for odd angular momentum. Okay, and yeah, you can understand this whole formula from 2D. This is the JT, and this -1 to the J comes from the U1 action. And this is what I said before. So this lambda would be this, and alpha is 1/2. This is for the leading contribution. There are other SL2C black holes. The other SL2C black holes will contribute, will give you even smaller contributions. Okay. Okay, so this is the partition function. And the proposal is that in pure 3D gravity, you can trust the contribution from other defects. And that this contribution, that let me call this the Maloney-Witten part, we should add contributions from other defects, which are these, which correspond to geometries that when you look at them in 3D, they are smooth, but they are not connected to any classical solutions. So these are not saddle. There is no saddle point with. So each defect looks locally like a horizon of SL2C black hole, and there is no solution with more than one horizon. But what we argued in this paper is that in pure gravity you can trust these corrections, and we can see that they resum into a shift of the BTC extremality bound. So this is the same formula of JT gravity, but putting the values of the three-dimensional problem. So sorry, I had to go a little fast, but so yeah. So this is the picture. So this is the temporal circle, and this is the spatial circle. So these are the solutions. These are the SL2C black holes, and these are these extra non-classical solutions that we claim if you add, you will get the positive spectrum. And in 3D, they have a name. They are Seifert manifolds, and it's an open question that I'm thinking about to compute them directly from 3D. And I think this is probably doable. There is a paper of Beasley and Witten where they show that all Chern-Simons theories in Seifert manifolds can be computed by localization. So there is some hope that one might be able to compute all these contributions. Okay, so to summarize the story, so the solution for this negativity close to extremality is to include Seifert manifolds. The solution for this negative density of states at spin 0 needs a new calculation. So this at J equals 0, so we cannot use the JT gravity approximation. And the solution to the continuum spectrum for pure gravity, well, we can conjecture that this will be related to some ensemble average of 2D CFTs that should be understood. And it's not clear what ensemble of CFT means, but the hope is that if we include other topologies, such an interpretation will emerge. For example, in this paper of Kotler and Jensen, they compute this geometry in 3D. So this is like a torus times an interval. And they get something that looks very close to a 3D version of the JT answer. That definitely breaks factorization. So this also points towards this idea that the dual of pure gravity might involve an average over CFTs. Okay, so I was going to talk about higher dimensions, but I definitely don't have time. So let me, if you have any question, I'm happy to answer. The idea is just that the same dimensional reduction in the throat works in the same way. But the only difference now is that instead of having a U1, we have an SU2 gauge field from fluctuations of the transverse sphere. But the density of states has the same form without the gap. Let me mention quickly some work in progress where we repeat these calculations for a near BPS black hole in 4D. In that case, the theory in the throat is n equals 4 super JT, and this can be solved exactly in the disk, and it has a density of states that looks like this. So it actually does have a gap, and it has a delta function at extremality. So we thought that that's very interesting because this is consistent with the calculations that people did in string theory. This is the exact density of states, and it would be nice to understand this better. But okay, I guess that's it. So some open questions. I think this opens some interesting thing to analyze. For example, can we understand these one loop corrections, these quantum effects better from a higher dimensional perspective? We should be able to in 4D compute them from without having to resort to this dimensional reduction. That would be nice to do. And hopefully to extend to supersymmetry we already extended, but extend it to Kerr black holes. In the case of Kerr, the reduction is very complicated, but hopefully maybe 5D one can do something. And okay, and here's a list of applications. Is that for 2D CFTs, 3D gravity, and let me finish by mentioning that there is also similar setups in cosmology where one has similar quantum effects becoming important. But okay, maybe I should end here. Thank you.
Thank you very much, Joaquin, for the very interesting lectures.
Yeah. Sorry, I had to rush a little bit in this.
Sure, yeah. So are there any questions? I have two questions actually. So maybe you explained, but I didn't quite understand. So so the first is regarding this extremality, near extremality condition. So in principle, this Maloney-Witten partition function is valid away from extremality, right?
Yes.
So
yes.
Can you reproduce this, like, I mean, from 2D gravity? 2D dilaton gravity? Like, I mean, from this Achucar-Ortiz model?
Yeah, that's what, that was the point here. So when you look at the geometry and you reduce in the throat, you get ADS2 with a defect. And so from the point of view of the dilaton gravity theory, it's like you have to add a U1 monopole by hand.
Okay.
The idea is that both the U1 is singular and the metric is singular, but in a way that the 3D metric is smooth.
Right, but I thought, I mean, in the earlier discussion, you were talking about the near extremal limit, right? I mean, so whenever you're computing, like, I mean, this calculation that you did in 2 dimensions, so you were separating, like, I mean, the near horizon, the JT part and the classical part. I thought you were taking the near horizon limit there, the near extremal limit, sorry.
Yes. Yes.
So, and I'm asking, like, I mean, whether it's necessary to do that, right? Because, like, this 2D dilaton gravity model, I mean, it's also valid away from extremality.
Yes, I don't know how to do that in a way that gives you the same as Maloney and Witten.
I see, okay.
Like if I look near extremality and I look at JT and Maloney Witten answer, they match.
Right.
If I go away from extremality, I'm not sure how to do the calculation in a way that they're both consistent.
I see, okay. Okay, thank you. But, so, sorry, go on.
No, it's okay.
So, and the second one is, it's again related to this, so to the defect. So, I didn't quite understand how you connect the two discussions. So, in the previous lecture, right? I mean, you were talking about these defects, and that allow you to deform the JT model.
Mm-hmm.
But now, like, I mean, if we look from this 2D dilaton gravity model that you get from 3D gravity,
Mm-hmm.
so can you view this like as some kind of deformation of the JT gravity?
Yeah. So the idea is that before I was integrating out the gauge field, and I was assuming that the gauge field was smooth everywhere. And
Okay.
that gave me JT. When you look at the theory around the SL2C black hole, that tells you that you need to also include U1 configurations that are singular. And now the deformation, the deformation is to allow these monopoles or these instantons from the U1 gauge field to be present at different points of the metric. So I'm summing over any number and any location of these monopole insertions.
Right, but
yeah. So one comment from the U1 gauge theory point of view, you have to add them by hand. They're like disorder operators, right? Like you decide that now you do your path integral where you allow certain kinds of singularities, and the motivation to do that is from the 3D perspective that they are geometries that should, they are completely smooth and should be included.
Yeah. But right, so I guess, I mean, it's not obvious to me exactly how, I mean, this should correspond, I mean, the insertion of these defects, right? I mean, it should also correspond to the fact that you change the potential, right? I mean, you go from the JT gravity to this slightly different version, right? I mean, the model that you get from 3D gravity. But
yeah.
But I guess, I mean, the argument is I mean, effectively, like the gauge field changes the potential. Is that?
Yeah, that part you can do the same. Yeah. So you can say, yeah. So one way to phrase it, that we phrase it in the paper, is that imagine you fix the angular momentum in all the boundaries, you integrate out the gauge field, and then the net effect is to, when you resum over defects, is to end up with this dilaton gravity with a modified potential.
I see.
Yeah.
Thank you.
Yeah. So that just different descriptions of the same physics.
I see. Any other questions?
Can I ask a question?
Yes.
In your conclusion, can I see your last page?
Let me find it. Yeah. Okay. This.
Yeah. So in your application, you said not necessary hologram as well. Can you explain more?
Yeah, sorry. Yes, I didn't emphasize it too much. So I assume that the 2D CFT has a twist gap, but I didn't have to assume that it's large. And when you talk about holography, you assume that the twist gap is large, is related to having a local bulk. So this is what I mean is you have this Schwarzschild sector emerging from 2D CFTs that are not holographic. So you have theories where not holographic in the sense that they are not dual to something that is local and all that. And that has the same flavor as SYK, right? Where you have a theory that it's dominated by the gravitational Schwarzschild mode that controls the thermodynamics and the chaos. But other than that, the theory is very far from having a local bulk dual, because you have this tower of states that have very order one anomalous dimensions and all that. So it just seems interesting that there might be a similar picture in higher dimensions where you have theories that are very complicated, but this JT limit becomes this kind of double scaling limit of large charge and low temperature might still be described by JT gravity. Yeah.
Oh, I see. So you mean it's more universal than just holography, right?
Yeah, that's what I would expect from the bulk argument, and in the case of 2D CFTs, from the boundary argument as well.
Okay, thank you.
Yeah. Here I also, another reason why I put this here is because it would be interesting to if one has a model where one can see the emergence of the Schwarzschild mode, like you do in SYK, with you put the mean fields, G sigma action, and you have the emergent symmetry, and it would be also nice to understand how this symmetry emerges, this conformal symmetry emerges from theories that are in higher dimensions, in a way similar to SYK, but in higher dimensions.
Okay, thank you.
Mm-hmm.
Any more questions? If not, let's thank Joaquin again for the very nice lectures. And now we take a